Hello everyone, we have here two examples of refrigeration cycles, ideal vapor compression cycle. For our first example, a Carnot refrigerator requires 1.3 kilowatt per ton of refrigeration to maintain a region at low temperature of negative 38 degrees Celsius. Determine first the coefficient of performance of Carnot refrigerator, the higher temperature of the cycle, and the heat delivered, and the COP when this device is used as heat pump. For given we have the final temperature of negative 38 degrees Celsius, we will add 273 to make 235 Kelvin. The power required per ton of refrigeration is 1.3 kilowatt. For our COP of current refrigerator, we will just divide the heat absorbed over the work done, or the 1 ton over the 1.3, or the 14,000 kilojoule per hour over the 1.3 times 60 times 60 kilojoule per hour to have 2.99 as our answer. And for our higher temperature of the cycle, we have here some illustration. We have here TS diagram, and from the equation, coefficient of performance of Carnot refrigerator equals to the final temperature over the initial temperature minus the final temperature, or the 2.99 equals 235 minus initial temperature minus 235. We will derive it to have initial temperature is equals to 235 over 202.99 plus 235. We have 313.6 Kelvin, and we need to convert it to degrees Celsius. We have 313.6 minus 273, we have 40.6 degrees Celsius. And now for our heat delivered as heat pump, we will add heat absorbed plus the work done. For the heat absorbed, we have 14,000 kilojoule per hour over, or divide 60, plus a 1.3 times the 60 minute over 1 hour. We have 311.3 kilojoule per minute. And for our coefficient of performance of the heat pump, we will divide heat delivered over the work done, or the 311.3 kilojoule per minute over the 1.3 times 60. We have 3.99. For our second question, a refrigerating system operates on the reversed Carnot cycle. The higher temperature of the refrigerant in the system 35 degrees Celsius, and the lower temperature is negative 15 degrees Celsius. The capacity is to be 12 tons. Neglect all losses. Determine the coefficient of performance, the heat rejected from the system per hour, and the power required. For the solution, we have the initial temperature 273 plus the 35 degrees Celsius. We have 308 Kelvin, and for our final temperature, we have 273 minus 15. We have 258 Kelvin. The capacity is 12 ton, and our coefficient of performance, we have formula final temperature over the initial temperature minus the final temperature, or the 258 over 308 minus 258. We have 5.16. For the heat rejected from the system per hour, we have the coefficient of performance is equals to refrigerating effect over the work input, or the 5.16 is equals to 12 times 4000 kilojoule per hour over the work input. Since we will looking for the work input, we'll derive it, and we have now equals to 12 times 14,000 kilojoule per hour divide 5.16. We have 32,558 kilojoule per hour. Thus, heat rejected per hour, refrigerating effect per hour, plus the work input per hour, or 12 times 14,000 plus 32,558. We have 200,558 kilojoule per hour. And for our power required, we will divide work input per hour over 60 times 60 minutes per hour, or the 32,558 over the 60 minute per hour times the 60 equals 9.04 kilowatt.